So, teams from the Graz University of Technology, whom we have spoken of before, KU Leuven, and Cyberus Technology have been at it again. And if we ever wanted, as I mentioned at the top of the show, a perfect example of Bruce Schneier's sage observation that attacks never get weaker, they only ever get stronger, we have it here. What these guys have done quietly, although they've known for a year, none of us have, they have been sitting probably impatiently on this, is a truly significant advancement to the practicality of what was the mostly theoretical attack on speculation and micro-architectural performance boosting that we began talking about right from the start of last year. So the term microarchitecture is all throughout this. So let me just explain. The architecture is what the code that runs on the processor sees. So it's the registers, it's the stack, the various execution units. It's the view that the processor provides to the code. It was quite a while ago that stopped being the only architecture in the chip, especially for the Intel chips, because the instructions are so complicated that as they kept adding new features, the idea of designing this instruction set, implementing the instruction set as gates, just as simple logic, became impossible, especially when they started wanting to get really fancy. So what happened was they created a processor inside the processor. The so-called microcode. So that runs, the microcode runs on the microarchitecture, which is this processor running at the clock speed that is given to the chip, the 3 gigahertz or whatever it is, and that processor essentially implements the instruction set that the outside world sees. So, and that's how when Intel produces an update to the firmware of the chip, that's the microcode that implements this. And so that's what so for example, when they talk about microarchitectural data sampling vulnerabilities, the lid that's been torn off of the Intel architecture, unfortunately, is that there are all kinds of, because you have a processor in a processor, because there's a whole nother dance going on separate from the one that's public. All of the attention up until now has been on the security of the public processor. That is, it's been scrutinized and it's been looked at and it's been validated as secure. Nothing leaks at that level. But as soon as we started looking past that, we got the Spectre and Meltdown problems at the beginning of last year. So this is just, this is so tasty for researchers. No one who's really into this has been able to put it down. And what came to light last Tuesday morning, as this podcast was already set up and ready to go, was essentially, I would say it's more than the next shoe to drop. It's an anvil dropped, because what happened was the change from theoretical to absolutely proven. This is probably why Intel was really in a panic. The Intel has known of this for a year. And so the good news is, they've taken responsibility. Oh my God, I would do anything to be a fly on the wall to know really what has been going on inside their meetings, because it has to be some serious discussion about how they got into this position and how these problems occurred. But anyway, what we have now, after more than a year of trouble, is the so-called, it's sort of been generalized to microarchitectural data sampling vulnerabilities. And to that original work, which first brought us Meltdown, we have on this site, cpu.fail, has ZombieLoad, that we had fun just saying last week. We have something called RIDL, Fallout, and store to leak forwarding. Each of those is a different exploitation of subtle features of Intel processors, which have been produced over the last 8 years, since around 2011, which as a consequence make it extremely difficult for the processor, to keep its secrets as it was always designed to. That is, until the beginning of last year, we had these processors sitting on servers in cloud environments with VMs sharing a single core among any random set of parties, whether friendly to each other or not. That all changed at the beginning of last year, because it turns out that it was at that time, it was theoretically possible. A couple examples were shown. Mostly it was done like, goodness, here's a problem. We need to fix this before it's too late. Well, what we got just last Tuesday in the form of firmware updates for the microarchitectures at some significant performance hit. I've seen some benchmarks that look like it takes maybe 10 to 12% off the top, which is a chunk of performance, because unfortunately, as we've seen, in order to these problems are a result of the past of other threads of execution leaving trails, leaving hints in the microarchitecture, which clever researchers are able to tease out over time. And again, these attacks have only gotten better. Okay, so ZombieLoad, I'm not going to go into infinite detail, but because I just want to give our listeners a sense for this. ZombieLoad resurrects private browsing history and other sensitive data. It allows the leakage of information from other applications, from the operating system, across virtual machine boundaries in the cloud, and from trusted execution environments. The RIDL attack allows the leakage of information across various security domains from different buffers, such as line fill buffers and load ports. Those are microarchitecture attributes that are not surfaced at the processor level, but they're all part of the plumbing that's going on behind the scenes. RIDL demonstrates attacks on other applications, the operating system, virtual machines, and trusted execution environments. So there's a lot of overlap between these, but they're different types of attacks against different facets of the microarchitecture. The Fallout attack allows reading what the operating system recently wrote and figuring out the memory position of components of the operating system, thus strengthening other attacks. In other words, it helps to defeat KASLR, kernel address space layout randomization. And finally, The store-to-leak forwarding exploits CPU optimizations introduced by another microarchitectural component, the store buffer, to also break address randomization, monitor the operating system, or to leak data when combined with some aspects of Spectre. Spectre created these gadgets which were little pieces of code which were used. Store-to-leak forwarding is able to reuse some of these Spectre gadgets, essentially making the attacks stronger. Microsoft, for their part, last Tuesday on May 14th, wrote, on May 14th, Intel published information about a new subclass of speculative execution side channel vulnerabilities known as microarchitectural data sampling. And of course, now we know the data being sampled is somebody else's data. If you happen to be sharing an Intel processor with somebody else. Microsoft said an attacker who successfully exploited these vulnerabilities may be able to read privileged data across trust boundaries. In shared resource environments, such as exists in some cloud services configurations, these vulnerabilities could allow one virtual machine to improperly access information from another. So this is, sounds like a repeat of what we've been talking about all of last year. In non-browsing scenarios on standalone systems, an attacker would need prior access to the system or an ability to run a specially crafted application on the target system to leverage these vulnerabilities. What they didn't explicitly say is that code running in a browser is able to determine what the browser has been doing. So it's a potentially significant privacy violation just using a browser at the browser level. So they allocated, or I should say the CVE system allocated 4 different CVEs, microarchitecture store buffer data sampling, which was given the acronym MSBDS, microarchitecture fill buffer data sampling, MFBDS, microarchitecture load port data sampling, MLPDS, and microarchitectural data sampling of uncacheable memory, MDSUM. So over on the CPU.fail site, they did a little Q&A to sort of help demystify this. They asked, am I affected by this bug? The answer, most certainly yes. Are these software bugs? No. These bugs are in the processor. Software can work around these bugs, which costs performance. Future processors will have integrated fixes, and that is no doubt true. They ask, can I detect whether someone has exploited this leakage against me? They say, we have no data on this. The exploitation may not leave any traces in traditional log files. Can my AV detect or block these attacks? They said, while possible in theory, this is unlikely in practice. These attacks are hard to distinguish from regular benign applications. However, they write, your AV may detect malware which uses the attacks by comparing binaries after they become known. They ask, has this been used in the wild? And they answer, we don't know. So they wrote a 16-page detailed paper that I'm not going to drag us through. And I've already pretty much explained what I had here in the that I quoted from the abstract at the top of the paper. They conclude, though, saying, with ZombieLoad, we showed, and this is in these 16 pages, in ZombieLoad, we showed a novel meltdown type attack targeting the processor's fill buffer logic. ZombieLoad enables an attacker to leak recently loaded values used by the current or sibling logical CPU. We show that ZombieLoad allows leaking across user space processes, CPU protection rings, virtual machines, and SGX enclaves. We demonstrated, and they did this, the immense attack potential, and that's what has changed. The takeaway here is this went from being, well, okay, yeah, in theory this could happen. This research changed this to making these practical attacks. They said we demonstrate the immense attack potential by monitoring browser behavior, extracting AES encryption keys, establishing cross-VM covert channels, and recovering SGX sealing keys, Intel's secure enclave. Finally, we conclude that disabling hyperthreading is the only possible workaround to mitigate zombie load on current processors. So, for what it means to us, as I said, this is primarily a further collapse in inter-thread isolation. Inter-thread isolation only matters if one way or another a system has a malicious thread running on it. In the case of a user's machine, a malicious thread we would call malware. In that case, you've already got malware on your system, and so you're in trouble. This could be a way for malware to extract encryption keys from your system. Like, for example, if you were using BitLocker, and depending upon BitLocker's encryption of your hard drive, it would be possible for malware to reach into the kernel to get the key that it would not otherwise have access to because it would be well protected, and then make off with it or send it somewhere, use it, do whatever it wants to. So, but in general, once you've already got a malicious thread on your system, you're already in trouble. The real problem, as I've mentioned, is in the cloud environment, where you might very well have a huge heterogeneous environment with a data center full of servers that are just mixing and matching and running anybody's code on any piece of hardware, moving VMs about without any concern. That's the way a lot of these systems are set up now. The problem is a bad guy gets in there on a system that has not been mitigated against this set of problems, and you've got trouble. I know under Linux, with these patches applied and a state-of-the-art Linux, I've seen some benchmarks that look like it takes about, as I said, about 10 to 12% of performance right off the top. It looks like it's a larger hit on the later processors, because the later processors more thoroughly take advantage of sophisticated microarchitecture in order to speed things up. So, as I said, my subtitle was "Speeding Up is Hard to Do." Basically, I don't know what Intel is going to do. They're probably, what it means is that we're going to have to build into our operating system some explicit flushing or maybe an additional level of blinding between threads. Right now, there is very little thread isolation between hyperthreads, because hyperthreading is basically a second set of registers that you do a very fast context switch from one bank of registers to the next. It was a clever, very inexpensive way of allowing a processor to continue running when it would otherwise have had its thread stall waiting for something. Intel said, hey, wait a minute, with almost no additional logic, we can create a lightweight context switch just by, creating a second logical thread on the same hardware. Yes, they were right, but boy, you don't want to have that other thread sharing the same core, which is what happens. You don't want to have it be malicious. So already we have this notion at the architecture level of context switching. That's what we do is, when we push all of the threads on the stack and then load the all the registers from a different thread that has been stopped. That's a context switch. What I think we're going to end up seeing is Intel having to, in order to save the fundamental design of their chips and implement a system which is secure, we're going to have to get something like a context switching mechanism at the microarchitecture level. It should have always had it. Nobody was looking, and nobody was this clever about, and I guess really appreciated how much information could be obtained from little subtle variations in timing. At this point, it really breaks the barrier certainly between hyper-threaded, a pair of threads running on the same core. And of course, as we know now, since cores share caches and we're able to probe cache contents, nothing is safe. So at a cost of performance today, we're getting firmware updates. Microsoft has said they're only going to be doing it for Windows 10. So if you are running Windows 7 in an environment where you're at risk, and again, there's a bunch of caveats, in an environment where you're at risk, then it's worth updating your BIOS. I mean, I guess in general, there's no reason not to update your BIOS is available from your manufacturer. But unless you are in an environment where you really are running threads that have a probability, a likelihood, a reasonable possibility of being malicious, if that's not your environment, all of this is interesting and it's being fixed for you, but probably not it should not be a source of great concern.